much, Paul and Steve, for that nice introduction, and thank you, North America, for the opportunity to give a talk today about the role of drip suppressants. Basically, what I feel is a critical market need and an unmet, basically market need as well. We'll talk about some of the new things that are occurring there. Next slide. So here's a brief outline. Basically, I'm going to go in a little bit different aspects with regard to Pinfa North America. But then we'll be talking about some of the mechanisms of flame retardancy and how drip suppressants work and how they work together with halogen and non-halogen flame retardants. We'll talk about some of the regulatory developments that have been affecting this area and talk about current non-halogenated solutions as well as alternatives for the future and what the status is there, and then some conclusions and outlook. Next slide. So they'd already heard some comments about PINFA, basically the Phosphorus Inorganic Nitrogen Flame Retardant Association, a nonprofit organization whose goal is basically supporting fire safety globally and continuing to improve the efficacy, environmental health and safety, and sustainability of the flame retardants, and educating people like this in this webinar to how to use these materials successfully in their applications. Next slide. Yeah, a key thing that being a member of PINFA and access to these things, but also you can access these particularly is the PINFA FR product selector, and you can see the website to go to. It has information for over 65 commercial non-halogen flame retardant products. It's really a very excellent guide. For instance, if you're trying to flame retardant polypropylene, what are the products that are available? It's also the flame retardant application brochures per markets, for instance, in electrical and electronics, building, construction, transportation, etc. A very key one here is the free monthly newsletter. And you can see you can sign up. You only need to sign up once, but it really is a fact-filled monthly update on FR materials, market developments, and regulatory updates. PINFA also, does sponsorship and educational outreach to not only to itself, but obviously to related associations like the SPE, which we'll be talking about at the end of this presentation. We have something coming up in January, as well as SAMP and other organizations as listed. And we do participate, for instance, with the AMI FR conferences as well. We have also had industry workshops with a market focus, for instance, focusing on aerospace and transportation, building construction, and electronics and electrical as some subjects. We've also had training. In fact, we had a webinar with how basically the basics of non-halogen flame retardants and then how to formulate those types of materials. We had various speakers, myself included, and others, as well as suppliers. So these are some of the key things that PINFA does to basically bring the market information, technical information to the users such as yourselves. Next slide. Okay, let's start into this for the technical portion of this webinar. Flame retardants, and I think a lot of this, a lot of people are already aware of this, but I think it's fair to go into this here again. Flame retardants are not meant to make a material non-flammable. Okay, I mean, basically, what they do is they prolong the amount of time till basically the ignition spreads and the fire spreads. So really, you can see on this timeline, you see temperature on the y-axis, and then on the x-axis is time. So typically, a start of a fire, for instance, an overloaded circuit breaker or an outlet, etc., is basically tending to not let that fire progress, maybe extinguishing at that point in time. If it does a little bit more, it typically tends to delay the amount of time till you get to the so-called ignition, and fire actually does start spreading. It's so-called getting into this area of flashover. And flashover is typically when you generate enough combustible gases, let's say in an enclosed area like in a living room, etc., that the material does basically combust. A flame retardant does is allows you this time between, let's say, time 0 to flashover to get out of a building, or in the case of, let's say, enclosed areas like in trains or airplanes or subways, to let people egress and get out of the area where the fire is being developed. And then obviously you go into this other area here. But again, the key thing is for flame retardants to delay the amount of time and also minimize the amount of smoke and toxic gases that are generated in the very beginnings of a fire. And how's that done on the next slide? So basically, the combustion of plastics, I should have put it in here, but I think most people know the so-called fire triangle. And what that means is you need to have fuel, you need to have oxygen, obviously from air, and you need to have a heat source. If you take away any of those three factors, typically the fire cannot be sustained. So basically, the way that the flame retardants work are in two major mechanisms. One is so-called condensed phase, which is typically where the non-halogen flame retardants work. And then there's so-called gas or vapor phase mechanisms. And this is typically where the halogenated flame retardants work. Let's start with the halogenated flame retardants, and typically using a synergist like antimony trioxide, although other metals can be used as well. But that's typically the synergist that's used with halogenated flame retardants. This combination of a halogenated flame retardant and let's say antimony produces free radicals that act in the gas phase to terminate the combustion reaction. So they're very effective and they work in the gas phase. On the other hand, the non-halogen flame retardants, typically the phosphorus nitrogen flame retardants, as well as the inorganic hydrates, work in the so-called condensed phase. They work by a physical mechanism. So typically what occurs is you form a glassy char or a intumescent or foamed up char in the case of phosphorus and nitrogen flame retardants. And what that does is basically makes it more difficult for the fire to access oxygen, also impedes the flow of the combustible gases out where they can actually burn. The inorganic hydrates also work by basically like aluminum trihydrate or magnesium hydroxide. They actually go through an endothermic decomposition. They give off water and at these temperatures steam, which typically tends to dilute the amount of oxygen that's available for combustion. And also this endothermic reaction takes in heat, so it tends to cool the area of combustion. So again, the two major mechanisms here, as I said before, the phosphorus and nitrogen flame retardants typically work in the condensed phase, whereas the halogenated materials typically work in the vapor phase or gas phase. Both of these are the primary method of extinguishing combustion. Both mechanisms can and many times do use drip suppressants. And what drip suppressants do, we'll talk about on the next slide. So typically, you can see this on the diagram on the right is polyethylene burning, and you see the flaming drips. And this is the other issue, okay? And we'll talk about, it becomes even more of an issue when we talk about the Underwriter Laboratories 94 test, particularly in the vertical orientation. So what drip suppressants do is tend to basically impede or retard or prevent this dripping behavior. And the dripping can either be a burning drip or a non-burning drip. But the origins of melt dripping is when you obviously heat up a polymer, you're heating it above either the glass transition temperature for an amorphous plastic or above the melting temperature for a semi-crystalline plastic. In both cases, the viscosity, the melt viscosity reduces or diminishes, and basically material can drip. You also get polymer degradation during combustion, so you're breaking down the polymer into smaller units, which again are less viscous and tend to drip. And again, both of these types of mechanisms going on reduce the melt viscosity, as I indicated before, and it also producing a more flammable, low molecular weight species during this degradation. And it's very evident when you see polyethylene. You can see it's degrading, it's breaking down, and you can see these flaming drips. You don't obviously don't want to have this happen in an actual fire, and you don't want this to happen when trying to pass, for instance, the UL 94 vertical orientation, or for that matter, even in the horizontal orientation, which takes us to the next slide.
So this, I think many people are familiar with the so-called standard UL94V test. And you can see that you've got a Bunsen burner here with a given amount of heat output and a certain height of the flame. And you can see that you've got this bar in the schematic here in a vertical orientation. And you obviously bring the slide the burner over to it, hold it there for 10 seconds, and then pull it away, and then take it back again. And what you're looking at is, how long does it take for the combustion to extinguish? How long is the flame burning, and then calculate those, add up those number of seconds. The other very key thing, as you can see in this UL94 test, is there's a wad of cotton. I've circled that in red at the bottom. And what you don't want to have happen is that if the material does start to drip, that drip impinges onto the cotton and starts the cotton on fire. Now remember that typically this test utilizes 5 specimens, and then you have 2 instances of bringing the burner to the specimen. So you basically have 10 opportunities for a potential drip, and particularly a potential drip causing the cotton to burn. No matter what the extinguishing time is, obviously you want to have the extinguishing time be as low as possible. But if you do get a flaming drip which ignites the cotton, you can see that you move to a classification of V2, which is an inferior to V0. V0 is what people are typically striving for, and you can see that the extinguishing times are very low, or lower than, let's say, for instance, V2 or V1, and you'll note that there is no flaming drip. So the intention is to have materials pass the V0 classification. And again, to point out that just only one instance out of 10 basically shifts you to a V2 classification. That's a very key thing to keep in mind. And now you can see why having a drip suppressant and making sure that the material, the formulation that you have, not only extinguishes quickly, but also does not have flaming drips. Next slide. We'll get into, what are some of the materials that are used out there. But as a background here, the regulations are very much a part of doing formulating and working in flame retardancy, and an increasingly focused, scrutiny on the halogenated flame retardants, and then more recently in the so-called PFAS type of materials. And PFAS, as you can see, is an acronym for per and polyfluoroalkyl substances. And these have come under increased global scrutiny and regulation. Due to these are so-called forever chemicals that are unfortunately very difficult to break down, and then they have spread, into the environment, and in some cases actually into people's bodies, etc. And so there's a lot of focus on these things, and not only on the materials that come under this classification, but also, for instance, for materials that are manufactured by using PFAS type materials. A lot of these PFAS type materials are perfluorosurfactants that are used to make fluorinated polymers, for instance, PTFE, otherwise known as one of the trade names being Teflon. So you can see that, as you'll see in a moment here, how the sort of the regulatory focus on PFAS has affected drip suppression additives. Also, there is one certain class of type of strong acid salts that is a PFAS as well. It's typically used in polycarbonate that has come under scrutiny. So again, with that background, we'll move into the next slide and talk about sort of the drip suppressants that are going to be used. But before getting there, let's just talk about, who's asking to not have materials that don't either have fluorine or do not contain or do not use PFAS in their manufacture. Obviously, various brand owners, they want to have transparency to their customers and being able to guarantee that they are not using PFAS type of materials. Various third-party certifications like Green Screen, EPEAT, etc., also involved in this. Consumer demands, obviously, there's increasing consumer awareness of these issues, and various NGOs and advocacy groups. In fact, looking at analyzing and pushing for certain flame retardancy bans. This is on the UN environmental landscape as well, and is part of the, in Europe particularly, and coming here is the circular economy. So understanding where these materials are and what's the fate of these materials.
So I also want to obviously want to come up with materials that are passing, the scrutiny of these various parties. The other key thing that's also driving this is, do we have these types of materials in the recycle streams? And then also in, for instance, the recycle streams, particularly from electronic waste as well, which is becoming more of a focus as well. Next slide. So indeed, the current anti-dripping material, basically drip suppressant of choice is PTFE. Again, one of the trade names is being Teflon from Chemours. But it's not all PTFEs that work as a drip suppressant. So-called fibrillating PTFE. So one of its crystalline polymorphs is basically such that when you expose it to shear, you can see that the material on the right-hand micrographs here, you actually form these fibrils, these microfibrils during extrusion and molding. And these materials are like little, like I said, the name implies, little filaments. And upon, putting this in the presence of a flame and heat, these things tend to contract very much like a rubber band does in the presence of a flame. And so it tends to pull the polymer mass away from the flame and inhibit dripping. So this is the mechanism by which it works. It's kind of unique to PTFE. Not much is needed to do this. Contents as little as 0.5% will work. In some cases, you do see it at maybe 1 or 2%. But I know, particularly in polycarbonate formulations, typically 0.5% works very well in passing UL 94 V0 in a polycarbonate system at 1/8 of an inch. Obviously, some of the technical problems have been in the past, and a lot of these have been dealt with, as we'll see here in a moment. Dispersion. Many times you'd get agglomeration from these materials when they came as a straight PTFE, fibrillated PTFE. Many times these materials had to be refrigerated because, again, it's a certain crystalline form that you don't want to have it changing to another crystalline form at higher temperatures. See, there's some of the issues earlier on. And obviously, the key issues now, though, are more of the fluorine and halogen containing, and now more that the PFASs are typically used during the production of these materials. Some of these technical issues, particularly with regard to dispersion and refrigeration, have been dealt with as the next slide. Indeed, encapsulation with a styrene acrylonitrile shell, so-called T-SAN, has really alleviated a lot of these issues with regard to agglomeration or the change in the crystal morphology. And indeed, these have been available for probably 30 years or so. Unfortunately, this does not, address the two issues that indicated in the previous slide, having to do that it is still a fluorine-containing system, and you typically do use PFAS-type materials to make the PTFE. So indeed, the goal here has been to see, are there any other halogen-free and PFAS-free alternatives that would have a similar effect, maybe by a different mechanism, but would also act as a drip suppressant. Next slide. So basically, from the patents and literature, some current work that actually I've carried out more recently, and we'll talk about here is, there's different ways to get this drip suppression behavior. One is physically by increasing the melt viscosity, such that the material does not have this tendency to want to drip. This can be done with the minerals, for instance, like talc, nanoclays, and some other types of minerals we'll talk about. Also metal hydroxides like magnesium hydroxide and aluminum trihydrate in sufficient levels will do that. There's also a physical and chemical, sort of a synergistic effect. Can you get this sort of increase in melt viscosity while also kind of charring the material? And for instance, branching the material such that you do get this increase in viscosity. There's some other methods as well, which is, again, more chemically accelerating this char or glass formation so that basically you're kind of encapsulating the melt so it doesn't drip. And this can be done by various types of materials, typically cross-linking promoters like zinc borate, silicones, some other materials as well that we'll talk about, as well as some ionomers, for instance, polyacrylic acid salts and PMMA So polymethyl acrylate ionomers and other ionomers as well. Also, intumescent type materials will, in some interesting ramifications of making intumescent type of materials, even coating inorganic materials, such that we do have an acid source, a char former, and a blowing agent. So there's many different types of approaches to developing this drip suppressant behavior, and we're going to dive into some of those in a moment. Next slide. I mentioned viscosity modifiers, talc being one. It's a naturally occurring clay mineral. You can see the sort of the chemical structure for this. It's a plate-like material, platelet material. Basically, you can see the references here: delayed and increased the mass, or delayed and increased the mass of drops noticed. So the key thing was delaying it and basically making sure there were not a bunch of small masses of drops. Again, I might point out that not all talcs are created equal. There's some materials that work better than others. So you need to talk with the suppliers, saying that I'm interested in using talc as a drip suppressant. As most people know, talc is also used as a major reinforcement in polymers like polypropylene, for instance. What this platelet material does is reduce the mobility of the polymer change, as well as reduces the mobility of gaseous materials to come out as well, hindering gas diffusion. Unfortunately, typically you need to use some fairly high levels to achieve the V0 rating in the UL94 test, so much higher than, let's say, a 0.5% in the literature and by my experience as well. The other key thing is that talc more recently has had some scrutiny as well with regard to how much silica content is in the material. So there's been some looking at that material as well, something to be aware of. Next slide. So here's a ramification of a type of technology here, again, using mineral silicates, other ones like velastenite, vermiculite, montmorillonite, which is the basis for nanoclays. But what I'd like to point out here is sort of a treatment for a mineral filler. And this is from Tulsa, and it's called the Addens, a trademarked type of material. And basically, they take this, if you go read their patents, is typically take this fibrous type of mineral, and then they impregnate it with some metal phosphates, etc., to basically to enhance charability and ceramification, or making the material turn more into like a ceramic during combustion. So at those temperatures, the material tends to sort of sinter together and turn into a ceramic. According to their data, a 2% addition can take a rating from, let's say, a V2, where it's got a flaming trip, to a V0 for a polypropylene system using an intumescent flame retardant. Now, remember, as I mentioned before, and I just want to reiterate, the drip suppressants are used in combination with some sort of flame retardant, typically a non-halogen flame retardant, or in some cases, a halogenated flame retardant. Typically, the drip suppressants by themselves at these low loadings will not necessarily act as a primary flame retardant, typically used together with some sort of primary flame retardant. Next slide. Again, we talked about the metal hydroxides or inorganic hydrates like magnesium hydroxide, aluminum trihydrate. And again, as I mentioned before, when we're talking about the mechanisms of flame retardants, these materials undergo an endothermic reaction, endothermic decomposition in the presence of heat, and they do that at different temperatures, typically magnesium hydroxide at a higher temperature than aluminum trihydrate. And they reduce gaseous water steam at that temperature, which cools the flame and also tends to dilute the amount of oxygen that's available for the fire. So again, that fire triangle is working in two areas there. Many times these materials are coated as well to help dispersion, but also to help them to form rather a protective layer to insulate the burning material, holding it in, preventing dripping, but also smothering or preventing the access to more oxygen coming in, and also preventing the escape of flammable gaseous decomposition products. But again, typically large amounts are needed. And again, you need to typically the effect of surface treatments to help the dispersion, as well as this drip suppression is also needed. Next slide. Again, char formers. Again, this is a typical intumescent type of mechanism here we'll talk about here, typically making a carbonaceous char. So again, you'll see later on, we'll talk about a non-carbonaceous char. But in this case, we're going to form a char that's primarily made from carbon. You can see the little schematic in the upper right-hand corner. When you heat a polymer, you can form a char, which many times will happen, similar to burnt sugar. But you can also form an intumescent char, and that's typically a char that has a foams type of structure. And typically you use a material, the three materials that are typically used to make an intumescent type of formulation is some sort of acid source, typically ammonium polyphosphate, but it can be other materials, some sort of source of hydroxy groups or carbon forming material, in this case penerythritol, but typically dipenerythritol and other materials, including carbohydrates, including lignans, as well as even starches can be used. But typically a melamine or a type of material that's going to form a gas so that you form this true intumescent char, which is basically a carbonaceous foam. And what that does is obviously this char prevents materials from dripping. It acts as a barrier from oxygen coming in and for flammable gases going out. And particularly when it's intumescent, you get this foam structure, which acts as a thermal insulator. So you've actually got several items going on here. These expandable chars resist the flame, and as I mentioned before, provide a barrier and insulate and mitigate the dripping behavior. Again, the three components that are needed for an intumescent char is an acid source, like the ammonium polyphosphate, which gives an acidic material upon heat, a charring agent, typically some hydroxy-containing material, as in this example, penerythritol, and then some type of a blowing agent, typically melamine or some other kind of nitrogenous material that typically gives off a nitrogen upon decomposition. Next slide. We talk about other char promoters like zinc borate. Again, it's a synergist. Again, you don't use zinc borate alone, but it typically what the zinc borate will do, it's a flame retardant synergist. It also helps prevent smoke and also works as a drip suppressant. Typically, the mode of action for the zinc borate is the zinc ion itself does work synergistically with phosphorus and nitrogen materials to tend to promote char formation. You typically get a borate type of glassy protective layer, even with the zinc borate itself, but particularly in the presence of phosphorus compounds, you actually get a boron phosphorus glassy material. It's generally quite impervious to oxygen coming in, and also impervious to having, let's say, flammable combustion products or flammable decomposition products going out to burn. And it forms some porous particles that prevent dripping, probably because of higher surface area, helping to absorb some of the melt. So it does work in a very, sort of multi-pronged approach. One of the potential issues here, it is a tier 2 health assessment, particularly in Europe, but also passing over here to the United States, having to do with boric acid and to some extent for zinc borate. So something to keep in mind. Next slide. Char promoters as well as silicones. Now, in this case, we're talking about a non-carbonaceous, typically, char. Basically forms a silicon-containing char layers or silica type of material. You can see some of the chemistry there. And this again, so instead of getting necessarily a black char, you're going to get sort of a white char. Again, provides more rigidity, so this drip doesn't it kind of holds that molten polymer in there, so it does not drip. It forms a pretty nice, basically non-permeable char layer, again, acting as a barrier to prevent oxygen ingress and prevents decomposition flammable gases from escaping and fueling the flame. Again, typically not all silicones work the same way, and there's typically certain molecular weights and typically a blend of the methyl as well as the phenyl substituted materials that work the best. There's been a lot of work in that area promoting on which materials work best. typically enables more cross-linking during combustion. And like I said, is synergistic with other flame retardants. Again, not all silicones work the same. And we'll talk a little bit later. Some of the issues here is making sure that the silicone material is compatible into your polymer. As you know, the silicones are typically very non-polar. And so you can have some compatibility during compounding and potentially even during at rest. You want to make sure that the silicone doesn't migrate out to the surface. So again, some things to keep in mind here. In fact, we'll be talking about one of the techniques that was employed by myself and others when we developed a way of doing this in situ. We'll talk about that later on from a drip suppressant viewpoint. Next slide. So other char promoters, as we already alluded to, were acrylic acid, basically salts and other ionomer derivatives. And you can see some of the mechanisms here on the upper right-hand or up to the right-hand side of the slide. Typically, what these materials do, these polyacrylic acid ionomers, they drastically increase the char formation due to the extraction of oxygen by the neutralized PAA. This is basically some of the mechanisms postulated here. Typically, again, not all of them, work the same way, and you typically need to have some sort of salt. Acrylic acid itself is not going to work. You need to have some salt, and it has been seen that you do see some differences, whether it be let's say a monovalent salt or a divalent salt like calcium. And again, I've seen examples where zinc works very well in coordinating with the polyacrylic acid. And you can see is the diagram here. This is some work that was done at Case, as a matter of fact, on a coating using some ionomers type of materials. And you can see, again, a very good example of an intumescent char. You can see that actually started as a coating, and you can see how greatly it has expanded. And again, provides a nice thermal insulation as well. Next slide. Here's a char former. This is a commercially available acrylic acid polymer and derivatives, typically and you can see some of the examples, and then you can go refer to this company called Paximer, and their materials, Paximer, the trademark, and you can see their reference to their patents and to their presentation. So basically, it prolongs the starting of the first drip. And again, by this cross-linking mechanism between the acrylic acid and the flame retardants used tends to mitigate dripping, reducing the amount of dripping. So it works as both a drip suppressant and synergist with a non-halogen flame retardants. Typically, they first started out in the polyolefins, and I know they've been working in developing some systems that work in the engineering polymers as well. So again, this is a good example of, again, an ionomer used as a drip suppressant. Next slide. Let's talk a little bit about some additional new alternatives and some things that I've been working on as well here. One of the key things, again, trying to be PFAS free and being more sustainable, non-halogen, including fluorine, is looking at nature and looking at bio-based flame retardant additives that can potentially act as drip suppressants. And if you go through the literature and you see some references here to various saccharide-based polymers like polyphenols, lignans, cornstarch, actually some work that I've done, which was funded by the Iowa Corn Promotion Board, we'll talk about here, where cornstarch was used as a drip suppressant. There's all references also to another natural product called phytic acid. There's even references to the DNA working as a drip suppressant and potentially even as a flame retardant. I already mentioned lignin and proteins, and there's some other polysaccharides like chitosan, which again is derived from lobster shells and shrimp shells. So a lot of work is being looked at in the bio-based area. There's even certain proteins that tend to char and may act as drip suppressants. I think we've all had the experience of burnt toast or a burnt steak on the barbecue. So we're all aware that these natural products can tend to char, and the question is, can they char in the right manner to be used as a drip suppressant? And I'll be showing some data here in a moment. So chief amongst these filter, features is you would like to have some phosphorus and nitrogen in the backbone, or potentially, as you'll see here, even some silicon containing materials. We'll talk about glass flake in a moment. Potentially some sulfur in the backbone. This is some work from the literature, and obviously carbon that can be decomposed into a carbonaceous material that will basically prevent dripping by forming some sort of a network structure. As I mentioned, some silicon-based materials and nanomaterials and pre-ceramics are in the literature. Glass flake, I've done some work in that area where glass flake also does work as a drip suppressant. There's some more exotic materials like molybdenum disulfide nanosheets, POS in certain polymers, and I think a lot of people are familiar with this silicon-containing material. I've even seen work with the siloxanes as well. I think the other thing to keep in mind with all of these, though, is obviously cost and the how what amount of loading is necessary. Because at the end of the day, the cost of a formulation is very key. And usually, what I talk about is formulated cost. Obviously, which is equal to what is the price per pound for the material, but what's the percentage I need to use? So actually, what is the cost contribution to a formulation? Some of these, bio-based materials, basically they're in the, they're not being mass produced. For instance, chitosan is not being mass produced per se yet. So indeed, you have to kind of look at the pricing, et cetera. I'm happy to say that the cornstarch that I use is basically commercially available, and you'll see that here in a moment, and is pretty low cost. Next slide. Indeed, material here is bio-based green materials, is for instance cornstarch. It's a bio-based, cost-effective green material. It's actually the material that it was used in my studies, and you can see the diagram to the right here is basically this is PLA and non-halogen flame retardant based on ammonium polyphosphate, and then cornstarch. And indeed, this is the cornstarch. You can go to Walmart and buy this stuff and use it as is. So this is it was nice as it's readily available, and it's commercial, and it's fairly low cost. Did work in both PLA and in polyolefins, as I mentioned, using ammonium polyphosphate. The choice of the non-halogen flame retardant is critical, particularly with regard to color generation. But we were able to achieve a UL 94V0 in the PLA and some other polymers as well, and with minimal effects on the properties. For instance, tensile elongation, notched izod, and melt flow. So basically, I was concerned about perhaps the degradation of mechanical properties, because remember, obviously, flame retardancy is one key characteristic, but obviously you have to be working with the other properties as well. Some further optimization is planned, and again, I thank the Iowa Corn Promotion Board for funding this work. So basically, evaluating the use of the cornstarch as a drip suppressant. Next slide. One that's been around for a while is expandable graphite, again, based on carbon. This is typically graphite that's been intercalated with a strong acid, typically sulfuric acid. And then the excess sulfuric acid is washed away. So you have this black compound. And it's an excellent, basically material, because what happens is when the material is heated up, it expands greatly. I mean, typically 200, maybe even a size 300-400 times its volume. So in other words, in a thin coating, you'll have a material that's going to expand to several millimeters, if not even a centimeter. And the carbon itself, the graphite that's left, is fairly non-combustible, and you do get this very large intumescent type of structure that is a very good thermal barrier. And again, since it is a platelet-like material, it does have this barrier to gases, either oxygen coming in or flammable gases going out. So again, this is something that's been used for quite some time, and it's getting being looked at again. One of the negatives is obviously it works well if your system is going to be black, or you can tolerate a dark color. It's used a lot in, for instance, for protecting polyurethanes and seating and things like that as a coating. So it's been around for a while. Some other carbon materials, nanomaterials that are being looked at and have been used, and there's literature on that, are carbon nanotubes as well as graphene. Typically, the graphene provides a platelet-like tortuous path, again, a barrier for oxygen ingress, or basically flammable decomposition products from escaping and continuing to burn. It also tends to reinforce the char layer. Typically, you're going to be using it with a non-halogen flame retardant. I've seen it used a lot with silicones as well as with borates to reinforce that glassy char. Carbon nanotubes as well, and in combination many times with graphene, again as a reinforcement of the char to give you a more robust char. Because there are in certain tests where, for instance, in large scale tests for pallets and things like that, in fact, one of the tests where they actually spray on water, you need to make sure that you don't the water doesn't break down that char and then basically release flammable gases and allow oxygen ingress in. So in many of these types of systems, and depending on the test, the integrity or the strength of the char is very key. I've already alluded to it many times as the integrity of the char with regard to providing a very good barrier, not having pinholes and things like that, so that these pinholes would allow oxygen to ingress, as well as allowing degradation products to basically go out and catch on fire. So basically, the robustness and the integrity of the char is very key in a lot of these systems, and depending on the test. Next slide. Here's an announcement from Avakian, basically again showing the urgency or the need in the marketplace. As I opened this presentation with, is obviously the drip suppressant of choice has been PTFE, a fibrillating PTFE, and then I also stated further, the scrutiny and some of the pressures on elimination of fluorine and PFAS derived materials. So you can see here, basically it's an urgent market need, and in many cases I'd say unmet market need. This is a recent announcement from Avakian, in which they have a polycarbonate formulation that is formulated out without PTFE, and you can see that you can go to their website and read more about it. But again, this kind of points that the marketplace is reacting to a market need. Next slide. This is another thing that was actually done as well. We were talking about silicones, and this was work that was done at PolyOne, now Avakian, actually by myself, Zhao, at the time. So again, we mentioned sometimes the difficulty getting silicones into a polymer. In this case, we were basically replacing the perfluorinated strong acid salt as well as the PTFE. And the way to get the silicone into the material was actually making the silicone in situ via reactive extrusion. This worked very well in polycarbonate. There's actually an issued patent in this area, as well as in a polyphosphonate co-carbonate formulations as well. So again, a new approach to providing drip suppression. Next slide. FRX Polymers has also announced or developed a series of starting formulations to achieve UL94V0 in polycarbonate and in polycarbonate blends, such as with polyesters and ABS. And again, this is based on their trade name, Nofia polyphosphonate co-carbonate. And this is done without PTFE and is PFAS free. So you can contact them for more details. Next slide. So summary and outlook is basically the goal is finding a substitution for PTFE in halogen-free systems. And again, we've talked through and gone through some examples of how they work, the current systems, and what are some current alternatives and some alternatives that are in progress. So basically the physical viscosity modifiers, we've talked about various fillers. We talked about chemical char promoters, including cornstarch. We also talked about silicones. We talked about glass flake as a physical viscosity modifier. And we've even talked about some reactive extrusion approaches. Some new things that are being developed is continuing to look at carbon nanomaterials, as well as bio-based green materials, including proteins, etc. But there's also work at looking at, well, can we develop some lower cost, inherently flame retardant polymers? As you know, a lot of these polymers, like the polyether imides, the polysulfones, etc., are inherently flame retardant and really don't need any flame retardants or drip suppressants. Unfortunately, the price for those materials is much higher, but is it possible that we can develop some polymer systems that are much lower in cost but have those attributes as well? Next slide. So first of all, I'd like to thank you for your attention and acknowledge some of the people, for instance, the Iowa Corn Promotion Board for providing the funding for the work on both the cornstarch and glass flake. I'd like to thank Professor Gary Winnick for some discussions and some of the work that I presented here at Case Western Reserve. Thank Maggie Bauman at Performance Polymers and Additives and FRX, Yiming Yang, Yiming Jiang, rather, who is at Georgia Tech as a PhD student pursuing his PhD. And again, for Pinfa North America for the opportunity to present this. And obviously, we're going to go into some questions now, but you've got my email address if you have some further questions and need some clarification. Thank you. Next slide.